Analytical modeling of characteristic maps of the SR-30 turbojet engine. Abstract. A crucial step in the mathematical modeling of a gas turbine engine is the characteristic map development of its main components, the compressor and the turbine. Maps can be obtained from manufacturers, although they are generally not available to the user. Furthermore, the construction of these maps through experiments is expensive. Analytical models prove to be economically more advantageous. Compared to other methods, they require little experimental data to be validated. These models are based on physical principles, so the results are more accurate compared to those obtained through numerical simulations or the use of neural networks. This approach allows more flexibility to make changes to the performance characteristics of engine components. These changes may be achieved by modifying certain geometric measurements. This quality could be used in diagnostic and/or engine control systems. In this work, the characteristic map of the SR-30 turbojet engine components is analytically modeled. Geometric dimensions and properties of the working fluid were taken as data. This is an one-dimensional model in which it is analyzed the aerodynamics and thermodynamics parameters in each station of the centrifugal compressor and axial turbine. Design point calculations are used to estimate the values of working fluid parameters such as velocity, pressure, temperature, enthalpy, and entropy function. Results of this work are compared with those obtained by other authors. For greater reliability in these results, an experimental validation is necessary. Keywords: turbojet engine, characteristic map, analytical model, compressor, turbine. Introduction. Turbomachinery component performance maps constitute an essential input to the development of engine performance models. Maps may be obtained from experimental procedures, but this can result in an expensive endeavor. Furthermore, experiments might not completely describe the full range of interest, and the use of extrapolation is required. Manufacturers usually develop product component characteristic maps, but this information is rarely distributed to customers. In addition to experimental methods, there are other alternatives in obtaining performance maps. IJERT 1 used data from published maps to reproduce component maps through commercial programs such as Smooth_C2 and Smooth_T3. Lazaretto et al. 4 developed artificial machine maps using generalized maps taken from literature with appropriate scaling techniques. Results were validated with test measurements from real plants. Many authors have used neural networks approaches. Gustafsson Lal 5 obtained steady-state compressor performance maps from correlations of transient compressor maps. The learned correlations were expected to provide information for predicting stall and surge inception. UET 6 predicted an axial compressor performance map based on neural networks. Training was performed with experimental results provided from manufacturers. Gorbanyan et 7 used different types of neural networks to simulate the performance maps of an axial compressor. Data was obtained from a compressor rig test. Zhang et al. 8 developed an analytical model for the centrifugal compressor based on first principles where energy transfer is taken into consideration. The dynamic performance including losses was determined from the compressor geometry. In addition, incident and friction losses were modeled while the clearance, backward and volute losses were considered constants for all off-design conditions. Witkowski et al. 9 developed a one-dimensional analysis for the SR-30 gas turbine components used in education and research settings. Based on design point performance, the flow through the radial compressor and the one-stage axial turbine was computed. The corresponding initial conditions of the flow along with the dimensions for each component were used. Losses were estimated using Stadolat's equation for slip factor calculations. These calculations were only presented for a design speed of 78,000 rpm. Studies in developing the component maps of a SR-30 turbine were performed by various authors taking into consideration the design point analysis developed by Witkowski et al. 9. May et al. 11 described a procedure to obtain the velocity triangles for the characteristic maps of the SR-30 gas turbine. An iterative calculation in Excel was used, but the mathematical analysis to achieve this goal was not presented. Resulting maps were plotted using the Smooth C and Smooth T commercial softwares. The model has been used to monitor health operation of the engine. Based on the mean line analysis, Law A copyright owner DTAL10 developed the compressor characteristic curves. The results were stored in a line format to prevent numerical interpolation problems. These authors did not use a map for the turbine, instead, it was characterized using Staudola's ellipsis equations. Compressor and turbine losses were considered in the calculation of the velocity triangles. OETAL11 tested most of the loss models previously published in the literature. They found an optimum set of empirical loss models for a reliable performance prediction of centrifugal compressors. METAL12 cites these loss correlations for the calculation of the compressor map. In radial flow machines, like centrifugal compressors, the angular momentum imparted to the flow is reduced by a factor known as the slip factor. Von Bakstra AM13 developed a method that unifies the trusted centrifugal impeller slip factor prediction methods of Busemann 14, Stadler 15, Stanitz 16, Wiesner 20, X 17 and Xanady, reported by Dixon 18, in one equation. This equation, which is used in the present work, may be adjusted for specifically constructed families to improve the accuracy of the prediction. There is no compressor map or turbine map available for the SR-30 turbojet engine that has been validated using experimental data. The present work develops an analytical model of the SR-30's component maps. A one-dimensional approach is applied to perform the calculation at the design point performance. The final goal is to produce tabulated functions that may be introduced into an engine model. In addition, interpolation will be applied to obtain values of the dependent parameters such as the referred mass flow rate m, the pressure ratio PR and the efficiency. Analytical model. In this section, the analytical model of the component maps is described. The design point and off-design performance are conducted taking into account the limits of the engine operation. Design point calculations are based on iterative procedures. This consists on assuming a value of the axial velocity component, then, performing the calculations required to find the aerothermodynamic properties of the fluid and finally recalculating the assumed velocity. Iteration is finished when the difference between the initial guess and the calculated axial flow velocity is within the imposed tolerance. As a result, the value obtained for the remaining fluid parameters will be found. Compressor map and turbine map models are described separately. The properties of the working fluid in a gas turbine engine have a powerful impact on its performance. The working fluid, which passes through the compressor, is assumed as dry air, and the working fluid that passes through the turbine is assumed as the product of combustion, the mixture of dry air and kerosene fuel. Water content due to humidity is neglected. The correlations used for the fluid properties were taken from Walsh et al. 19. The equations required to find the energy losses in the centrifugal compressor was obtained from OETAL 11, and the loss coefficients in the turbine were taken from Dixon 18 and Cohen et al. 20. Moreover, the thermodynamic relations used are derived from the Mollier diagram found in Dixon 18. Compressor map. The SR-30 turbojet engine uses a centrifugal compressor. The analysis for the flow through the compressor is based in the one-dimensional steady flow analysis, in which according to Dixon 18, the velocity and density are regarded as uniform across each section of a duct or passage. By continuity, the mass flow rate, m, through the compressor is given by M1CA1A1-2I CA2I2I2DC2DCA2D2CA2A2, 1. In equation 1, Ca and A denote the air density, air, axial velocity and the cross-sectional area respectively. The subscripts 1, 2I, 2D, and 2 denote stations corresponding to the entrance to impeller, exit from impeller, entrance to vane diffuser and the exit from vane diffuser, respectively. These stations can be visualized in Fig. 1. Compressor maps will be developed from data points obtained from calculations of the performance parameters such as mass flow rate m, rotational speed n, pressure ratio PRC and isentropic efficiency C. For this purpose, velocity triangles are calculated initially at the design point. At this point, the mass flow rate and the rotational speed are m0.297 kg/s and n equals 78,000 rpm, respectively. In addition, the geometric data and input conditions published by Witkowski et al. Are used. The first velocity triangle, depicted in Fig. 2, is calculated at the impeller inlet. According to this triangle, the relation between the velocity vectors is given by v1 c1 u1, 2, where v1 and c1 are the relative and absolute velocity of the air, respectively. The term u1 denotes the impeller I velocity vector or tangential velocity vector. It is assumed that the air enters the impeller I in the axial direction, i.e. c1 ca1. The angle between the relative velocity and the tangential velocity is 1 equals 57. At the impeller inlet, known also as I or inducer, the effective diameter is defined according to d 0.5 d2 d2. 1 ton r. 3. Where dt is the diameter at the impeller I tip and doctor is the diameter at the impeller I root. The annulus area of impeller I is a d2 d2. 1 4 tons r. 4. u1 d1n, 5. u1 d1n, 5. The mean tangential speed at the inducer may be calculated by Figure 3. Flow diagram of the iterative procedure at the impeller inlet. HH1C2 10121 6. HH1C2 10121 6. Equations required to calculate CA1 are presented. The static enthalpy P may be obtained by. In addition, velocities at impeller I tip, ut equals dtn, and at impeller I root, or equals drn, may be found. It is important to check that the velocities at the impeller I tip, where h01 is obtained from a polynomial function, should be less than the speed of sound, mt1, to avoid breakdown of flow and excessive pressure loss. To calculate the axial component of the absolute velocity ca1, a trial and error process will be performed. Fig. 3 shows the iterative procedure followed to obtain the parameters at compressor inlet or station 1. According to this flow diagram, the density is calculated on the basis of the known stagnation temperature and pressure. From the continuity equation an initial estimate of the axial velocity ca1 is obtained. With this value and with the help of thermodynamic relations from the Mollier diagram, the density is recalculated, and the actual velocity is determined from the continuity equation. If the assumed and calculated velocities do not coincide, it is necessary to iterate until convergence is reached. Dependent on the temperature T01, i.e. H01 equals Fh, T01. The static pressure P1 is given by P. P101. 011. ER. 7. Here, P01 is the total pressure. The terms 01 and 1 are functions dependent on the temperature T01 and T1, i.e. 01 equals F, T01, and 1 equals F, T1. The air density may be calculated from the equation of state for a perfect gas, thus P1 1 RT 1 8. Where R is the gas constant for the air and T1 may be found as a function of the enthalpy P, i.e. T1 equals Fh, P. Finally, the axial velocity ca1 is given by m. ca1 1a1 9. Additional calculations are considered to obtain the relative velocity v1, v. c2u2, and the absolute Mach number, m. 1 abs. c1 111. RT. The velocity triangle at the impeller tip is shown in Fig. 4. According to Fig. 4, the air leaves the impeller tip with an absolute velocity c2i. This velocity has a tangential or whirl component cw2i and a small radial component cr2i, they are related by c2c2, 2iw2i r2i. 10. Under ideal conditions the whirl component will be equal to the impeller tip speed u2i. Due to the relative eddies in the impeller blade passage, the impeller exit flow angle differs from the impeller exit blade angle. A measure of deviation can be calculated using the concept of a slip factor. There are many correlations predicting the slip factor. Von Bakstra AM13 describes a method that unifies the centrifugal impeller slip factor. The prediction method of Dixon 18, that uses one equation, will be used. This equation is given by 1 F1 cos 0.5 OSE 11, where FO is a correction constant corresponding to the compressor. This value is adjusted to improve the accuracy of the prediction. The blade angle at impeller exit is denoted by the ratio given L/SE is known as the blade row solidity. The blade length L and blade spacing SER. Figure 5. Flow diagram of the iterative procedure at the impeller outlet. According to the diagram shown in Fig 5, static and stagnation pressures and temperatures have to be determined. Thus, the total pressure P02I is given by P02I P01 PR2I, 13. T. In equation 13, P01 is given as data and PR2I is the pressure ratio. Initially PR2I is guessed and then calculated. The stagnation temperature T02I may be obtained from a correlation function of the stagnation enthalpy H02I, i.e. T02I FH02I. The enthalpy H02I is given by determined with L equals RI/cos and SE equals 2 RI/NB. The 2I HH02I H0102I S01 2I 14 HHH02I H0102I S01 2I 14. Terms Ri and Re are the radius of the blade leading edge and blade trailing edge, respectively, and the number of blades is denoted by Nb, the area at impeller exit, A2I, and the blade. Where H01 may be obtained from a correlation in function of the stagnation temperature T01, which is given as speed U2I, are calculated with A2I D2I B2I and UDN. Data. The term 2I denotes the efficiency that is initially, respectively. The terms D2I and B2I are the impeller tip diameter and the axial width at impeller exit respectively. In terms of the slip factor and the blade tangential speed, the whirl component of the absolute velocity CW2I are guessed and finally calculated after some iterations. The stagnation enthalpy at an isentropic process H02IS is obtained by the correlation function H02IS FHT02IS. In the same way, the temperature T02IS may be given by the correlation determined with function T02ISF 02IS. The term 02IS is an entropy. T CW2IU2I 12 CW2IU2I 12 P 02 is 01 RL and 02I P 01 15 P 02 is 01 RL and 02I P 01 15. Function obtained by the following expression. Some designers consider the value of the radial component C2I the same as the inlet axial velocity CA1, Cohen ETAL20, but, in the current model it is obtained with an estimated value based on equation 10. The final value of the radial component is determined following an iteration procedure which is shown in Figure 5. Where the entropy function 01 is obtained using the correlation function 01 FT01. The static temperature T2i is given in terms of the static enthalpy pi with the correlation function T2i f pi. The enthalpy pi is T calculated with the expression HH1C2 2I0 2I2 2I 16. The static pressure P2i is given by PP0 2I 2I0 2I 2I ER 17. Here the entropy functions 0 2I and 2I are given in term of the temperatures T0 2I and T2I respectively, i.e. Figure 6. Velocity triangle at the vane diffuser inlet. In Fig 6, only the absolute velocity c2d and its components are present. The relative velocity vanishes because there is no moving element. To determine the 0 2if, T0 2I and ft. The density and the whirl component Cw2d of C2d, the conservation of the 2I radial component of absolute velocity are calculated using angular momentum within the vaneless diffuser can be P, RT, and C, MA, respectively. The Mach assumed, i.e. Cw2d R2d equals Cw2i R2i. Thus, the whirl 2I R2i 2I component of the velocity is given by. Numbers should be calculated to ensure that the flow does not exceed the velocity of sound. The performance parameters are also affected by losses that occur inside the compressor. The correlations used for the compressor losses were taken from OETAL22 and Zhang ETAL8. CR CW2I2IW2DR 2D. The area and absolute velocity are obtained from A2D equals. The pressure ratio and isentropic efficiency may be given. Procedure performed here is similar to that followed at the impeller exit. No further energy is supplied to the air after it leaves the impeller, so that neglecting the effect of friction, the angular momentum must be constant, Cohen ETAL20. The above implies that no work is done in the vaneless diffuser and the process is adiabatic. Thus, the following relation is obtained. Where Euler is the ideal specific enthalpy change of the working fluid which depends on the slip factor and the tangential velocity of the blades at the impeller tip. Thus, Euler U2. The term H represents the summation of all internal losses in the impeller such as incidence loss, blade loading loss, skin friction loss and clearance loss. The pressure ratio and isentropic efficiency is calculated in the same way as in the last stage. Although here, hint I is substituted by hint Vd which correspond to the losses in the impeller and the vaneless diffuser, as follows, hint Vd equals. Finally, calculations of the velocity triangle at the diffuser output are performed. Here, the whirl component of the velocity is found using conservation of angular momentum, which yields Cw2 equals Cw2d R2d/R2. The area and enthalpy denoted by HACT, is the sum of the ideal specific. The absolute velocity, magnitude, Ra2 equals 2R2b2 and enthalpy change and the parasitic loss correlations. The velocity triangle at the vane diffuser inlet is depicted in Fig 6. Obtain the velocities and the thermodynamic states are similar to the previous stations. Assumptions done for the station of vaneless diffuser may be applied for the vane diffuser, thus H02D equals H02. In the calculations of the pressure ratio and the isentropic efficiency, the losses through the entire compressor stage, i.e., impeller, vaneless diffuser, and vane diffuser, have to be considered. These losses denoted by hint T may be obtained by the velocity triangles corresponding to the off-design performance are constructed taking into account the mass, flow rate and rotational speed in the range of m equals 0a 0.5 kg/s and n equals 50,000-90,000 rpm, respectively. In the off-design calculations it is assumed that the absolute inlet velocity remains axial and the design point value of the slip factor was constant for all off-design conditions. Turbine map. The state route 30 is a single-stage axial turbine composed of one row of nozzles and one rotor. Figure 7 shows the nomenclature of the stages employed in the calculations, N refs to the nozzle and R the rotor. Ainley and Matheson correlations 18 were used to calculate the energy losses. These estimated losses will be useful in obtaining characteristic parameters such as the mass flow rate m, the rotational speed n, the pressure ratio PRT and the efficiency T. The operating conditions used in establishing the design point velocity triangles were m equals 0.3 kg/s and n equals 78,000 rpm. A mean annulus diameter is assumed in the calculations. This approach is valid when the ratio of the tip radius RT to the root radius RR is low, RT/RR equals 138. The turbine considered in this work meets this low aspect ratio. Moreover, we can consider the mean diameter equal in all stations because the difference between the station mean diameters are negligible. Thus, the effective mean diameter may be given by d equals 0.5 d2 plus d2. With the effective diameter and the rotational speed, the mean blade speed is u equals dmn. The mean annulus area is calculated by a equals d2a d2/4. Geometric dimensions and inlet conditions were. Figure 8. Velocity diagram of the axial turbine stage. Fig.9 shows the iterative procedure to calculate CA3. This procedure is similar to the calculations made at compressor inlet. Figure 9. Flow diagram of the iterative procedure at the nozzle inlet. Initially, the velocity CA3 is guessed. Then, the static temperature is found using a correlation in terms of the static enthalpy P, i.e. T equals Fh. The enthalpy P is extracted from Witkowski ETAL9. By using the geometric measurements of the turbine, a tip clearance of 0.54 mm was obtained. It is assumed that the stator blades have the same shape as the rotor blades. The fluid through the turbine is the air-fuel combustion products. Fig 8 depicts the velocity configurations at each station in this turbine. In a single-stage turbine the velocity at obtained by turbine inlet C3 will be axial, Cohen ETAL20, thus, C3 equals CA3, CA3 is the axial component of the velocity at turbine inlet or station 3. The value of this velocity will be taken as constant for all off-design conditions, where H03 equals FH, T03, FAR, and FAR is the fuel-air ratio. The static pressure is obtained using where 03 equals F, T03, and 3 equals F, T3. Similarly to previous cases, the density is calculated with 3 equals P3/RT3. From the continuity equation, the axial velocity CA3 is calculated by CA3 equals m/3am. Finally, the corresponding Mach number. The static pressure may be calculated by. Fig 8 shows the velocity triangle at the nozzle outlet or station 4n. It is assumed that the nozzle angle, 4n, and the angular momentum at outlet remains constant. Therefore, for all off-design conditions the deviation of flow across the nozzle remains constant, thus 4n equals constant. As a result, the relationship between the whirl component CW4n and the axial component CA4n, notation shown in Fig.8, will be constant according to the relation. Since no work is done, adiabatic process, by the gas in the nozzle, the stagnation enthalpy must be constant over the annulus at the outlet. Thus, H04n equals H03. Fig.10 shows the flow chart used for the iterative procedure to obtain the axial component of the absolute velocity CA4n, where the total loss coefficient in the nozzle is denoted by n. Neglecting the effect of friction, the critical pressure ratio is, in equation 29, is the throat width, S is the pitch and E is the mean radius of curvature of the blade suction surface. Equation 29 is for low outlet Mach numbers, i.e. 0. For COS1S. More details about this angle can be found in Dixon 18. Initially, the axial component of the absolute velocity CA4 is guessed using the equality CA4 equals CA4N. The whirl component of the absolute velocity CW4 may be evaluated by the density, and the axial velocity component are calculated using equations similar to the previous cases. In addition, the Mach number M4 may be found by the absolute and relative velocity can be found similarly as in the other stations. The static temperature is found by the analysis. The off-design performance is obtained varying the speed and the mass flow rate. The speed was varied from 5,000 rpm to 9,000 rpm and the mass flow rate was hint T equals hint Vd plus HID plus HSFD, where hint Vd represents the internal losses in the impeller and vaneless diffuser, HID is the incidence loss in the diffuser, and HSFD is the skin friction loss in the diffuser. Varied until the design value was reached, 0.3 kg/s. The deviation of flow across the nozzle is assumed as constant at all off-design conditions. Because 4N is constant, the losses across the nozzle remain constant for all off-design conditions. Results. Compressor map results of pressure, temperature, absolute velocity, and Mach number in the behavior of the design point are shown in Table I. The values presented here correspond to each station in the compressor. The analysis was generated using the stagnation enthalpy H04, under the rotational speed of 78000 rpm with a mass flow rate of 0.297 kg/s. The abbreviation, PW, means present work. The table shows that the highest stagnation pressure is reached at the impeller outlet, P0 equals 323 kPa. The pressure at the diffuser outlet is higher than the impeller inlet due to irreversibility. The compression work done by the impeller is accompanied by an increase in temperature, thus, the stagnation temperature at the impeller outlet is 446 K. This temperature remains constant through the diffuser. Static, where PRT is the total pressure ratio which is guessed initially and then calculated by PRT equals 03-04 SS/R. The entropy function 03 is obtained using 03 FT03 FAR. The stagnation entropy function 04 SS is given by pressure and static temperature gradually increase through the compressor. Thus, its maximum values are reached at the diffuser outlet. These are 249 kPa and 429 K. The Mach number corresponding to the absolute velocity is maximum, and less than 1, at the impeller outlet. The results obtained correlate well with Witkowski ETAL9. Calculations at impeller inlet, 1, are practically the same as those presented in 9. Result differences in locations 2I, 2D, 2 are due to the correlations considered in the present work. The highest percent difference, corresponding to the static pressure at the impeller outlet, obtained when compared to 9 was 9.6%. This is most likely due to the difference in the energy loss and slip factor calculations. In the present work, correction factors were used in the energy loss calculations. The slip factor formula used in the present work was different from that used in Witkowski at AL9. Furthermore, the coefficient F0 of the slip factor used was adjusted to obtain an appropriate value. By varying the mass flow rate, 0 to 0.55 kg/s, and the rotational speed, 50,000 rpm a 90,000 rpm, the off-design performance was obtained. Fig 12 shows the effect of variation of mass flow and rotational speed on the pressure ratio. Solid curved lines shown in Fig 12 are the rotational speed. These are indicated by dimensionless values that vary from 0.64, 50,000 rpm, to 1.15, 90,000 rpm. These speed lines are obtained by joining pairs of points formed by the pressure ratio and the mass flow rate. The ends of each speed line coincide with the minimum and maximum mass flow rate. Joining imaginarily the minimum mass flow of each speed line, it is obtained the surge line. This line is nearly at the left of the maximum efficiency line. Surging is associated with a sudden drop in delivery pressure, and with violent aerodynamic pulsation which is transmitted throughout the whole machine. The line joining the maximum mass flow points for each rotational speed is called the choking line, that is, no further increase in mass flow is possible beyond this line. Figure 13 shows the effect of variation of the rotational speed and the mass flow rate on the isentropic efficiency. Curved lines represent the rotational speed, indicated by dimensionless values. Speed lines values are the same as in Fig 12. The operating point of maximum efficiency on each speed line is approximately the same. Ideally, the compressor should run on the curve connecting these points. In Fig 12, 11 dashed lines intersect the speed lines at a single point. These are called beta lines. Information on mass flow, pressure ratio, and efficiency is extracted from each of these points. This information is taken in tabular form, like tables 2, 3, and 4. These tables may be introduced in a SR-30 turbojet engine model. This procedure is presented in another work. Values of mass flow rate, pressure ratio, and isentropic efficiency of the compressor are shown in tables 2, 3 and 4, respectively. The first column of these tables shows the enumeration of beta lines. In the second row of each table, the percentage values of the compressor rotational speeds are shown. Figure 14 compares the results obtained in the present work with those presented by May et al. 12. The last one, indicated in the legend as paper. 3 speed lines of the compression ratio versus mass flow rate graph were compared. The dimensionless values of these rotational speeds are 0.7, 54,000 rpm, 1, 78,000 rpm, and 1.1, 90,000 rpm. Results show a better match as speed increases. In the present work, when the compressor operates near the lowest rotational speed, the choking point is reached with a lower mass flow rate. As speed increases, results of speed lines between the two works match better. Table V shows comparative results between the present work, indicated by PW, and those presented by Witkowski et al. 9, indicated as REF 9. Results are obtained in the design point performance, that is, at a rotational speed of 78,000 rpm and a mass flow rate of 0.3 kg/s. As shown in the table, static and stagnation pressure decrease across each turbine location. The temperature is highest at the stator inlet. At this location, in the present work, the stagnation temperature is 973 K while the static temperature is 967 K. The Mach number reaches its maximum value at the stator output. This value is less than 1, near the transonic region, m equals 1, in both results. If m equals 1, choking will occur. Both results match closely at locations 3 and 4n. It was evidenced that Witkowski et al. 9 has a mistake in the results of static pressure and static temperature, at location 3. A great difference between both results is observed in the absolute and relative velocities, at location 4. This may be due to the tip clearance value used to calculate the tip clearance loss. In the present work a value of 0.54 mm was used. This value was obtained by measurement carried out in the compressor of the experimental module. In Witkowski et al. 9 a value of 2.44 mm was used. Off-design performance results are shown in figures 15 and 16. Figure 15 shows the isentropic efficiency and mass flow rate against the work parameter, dH/T equals, H4AP/T3. In Fig 15, each line represents the rotational speed. Colors identify the value of each of these speeds. As the speed increases, the maximum efficiency is reached at a higher value of the working parameter. For each speed, the efficiency remains approximately constant above a certain value of the working parameter. This behavior is due to the fact that the loss coefficients have a small variation in a wide range of incidence. Furthermore, This approximately constant efficiency is greater as the rotational speed increases. In Fig 16 it is observed that for each line of rotational speed, the maximum mass flow increases as the working parameter increases. An increase in mass flow occurs until choking conditions are reached. For all speed lines, choking occurs at the same mass flow rate and at a value of the working parameter greater than 100 jkg/K. In Fig 17, results of the present work were compared with those presented by May et al. 12, the latter named in the legend as paper. For this comparison, the relationship between mass flow rate and compression ratio was used. In this relationship, graphs of speed lines corresponding to 78,000 rpm are shown. The solid blue line is the one obtained in the present work while the red dashed line is the one obtained in May et al. Graphics are similar only in shape. The difference in the numerical values between both graphs is great. This is due to the fact that the maximum flow taken into account in May et al. 12 is close to 0.22 kg/s, while in this work 0.3 kg/s was considered. The value of 0.3 kg/s is more reasonable, since it represents the combustion mass flow that would be the sum of the air mass flow coming from the compressor plus the fuel mass flow entering the combustion chamber. Tabulated values of mass flow rate and isentropic efficiency of the turbine are shown in Tables 6 and 7, respectively. The first column of these tables shows the values of the working parameter, dH/T or simply dHT. The second row of each table shows the percentage values of the rotational speeds of the turbine. These values are the same as for the compressor. Conclusion. In this work, a one-dimensional analytical model of the compressor and turbine maps was made. The unified slip factor formula recommended by von Baxter AM13 was used. This formula was used in obtaining the whirl component of the absolute flow velocity at the outlet of the compressor impeller. In the compressor map calculations, the internal and parasitic loss correlations selected by OETAL22 were used. In both maps calculations, iteration loops were used to find the axial component of the absolute flow velocity. Many equations were obtained from the Mollier diagram of the corresponding component. Finally, tabulated forms of the compressor and turbine maps were obtained. The results of the design point calculations for each component were compared with that presented by Witkowski et al. 9, a significant match was observed. Off-design performance results were compared with those obtained by May et al. 12. These match well in the case of the compressor. Turbine results showed similar behavior with a significant numerical values differing. This is most likely due to fact that May et al. 12 used a maximum flow rate of 0.22 kg/s while the calculation performed used a value of 0.3 kg/s. This value represents the combustion mass flow, which would be the sum of both the air mass flow and the fuel mass flow entering the combustion chamber. In order to further improve the modeling of the component maps, the validation should be developed by using experimental data or with maps obtained from manufacturers. In addition, as-built construction details should be used whenever available.